Hey, everybody. This is Eric. I'm the lead radiologic technologist for Sterling Medical. I appreciate you logging on today and watching this. Over the weekend, I actually had a question come across Sarah Kane, who is an MA with us. She's actually studying to take her LRT exam. Good job, Sarah. Keep up the good work. And she had a question about X-ray physics and kind of how X-rays are produced. So I figured I'd hop on here and we'd do a quick tutorial or class on how X-rays are produced, how it goes from being plugged into the wall to ending up in the image receptor with an image on it. Okay, there's a lot of different things that happen between that point and the end point. But let's go over it a little bit, okay? Okay, here on the whiteboard, we've got kind of what looks like a jumbled mess, but it actually makes sense. And I'm going to show you how. So here we have the X-ray tube, okay? If you guys were to leave your workstation and walk into the X-ray room and look up at the X-ray tower, this is what you would see, okay? A big metal cylinder which houses the actual X-ray tube. Okay, we can't see the X-ray tube because it's inside the metal, but trust me, this is what's in there. Okay, you'll also notice that there is a white box in the room on the floor, and it houses a bunch of electrical stuff. Okay, those are actually generators, and generation of electricity is what enables us to take X-rays. So what happens is our generators are actually plugged into the wall. The wall sends electricity to that generator. That generator actually changes the alternating current, which it is, to a direct current and much more power, okay? Much higher voltage. So once that higher voltage is achieved, it sends it on over here to the X-ray machine or the X-ray tube, okay? Now you'll see that the X-ray, pretend anyway, that it enters right here at the cathode. Now the cathode end of the tube is the negatively charged side of the X-ray tube. Very important for you guys to know that the cathode is negatively charged, okay? The other main component is the anode right here, and it is positively charged, okay? And that's going to make sense why here in a minute. So what happens is the high voltage goes into the cathode and it heats up something that's called a filament, okay? A filament is a spring like looking thing, which is made of tungsten. And we know that tungsten is very high melting point, atomic number 74, just in case anybody wanted to know that. And it's very easy to manipulate into a spring type apparatus, which is what it is. So this is a side view of the filament. Here is a front view of the filament. There's actually two different filament springs, a small filament and a large filament, okay? And depending on what kind of technique we're using, it's either going to choose the small filament or the large filament. So what happens is it's hit with that electricity and a whole bunch of heat is generated right here, okay? So much heat in that negatively charged electrons are boiled off of that coil, that tungsten coil. Lots and lots of negatively charged electrons. This is what we call an electron cloud, okay? And the process of heating up those filaments to the point of releasing negatively charged ion or electrons is called thermionic emission. Okay, that's another one you need to remember. Thermionic emission. It's the heating up of the tungsten filament producing negatively charged electrons, okay? So here we have these negatively charged electrons that have been boiled off due to high voltage, okay, from our step-up generator. Now, you'll note that the cathode is negatively charged and the anode is positively charged. So what happens between negative and positive, right? Okay, negative and positive attract. Okay, negative and negative repel. Positive and positive repel. Negative and positive attract. Okay, this is what we call a tube potential or voltage difference, okay, between positive and negative. So our tube potential is actually gauged by our KVP. The higher KVP we give a film, the more electrons are going to be released, right? And as what happens is these are negatively charged and they're propelled towards the positively charged anode or the focal spot right here. So we've got acceleration of electrons coming across until they meet the focal spot or the target of the anode, and it's a sudden stop. Okay, now in that very moment, that's when X-ray photons are developed. Now, that being said, only about 1% of the negatively charged electrons are produced into X-ray photons. The other 99% are dissipated in heat. Okay, so us trying to take an X-ray, 99% of what we do just turns to heat. Okay, 1% turns to X-ray photons, which allow us to take our image. Okay, but yeah, thermionic emission, tube potential, where electrons are coming across there and they're going to hit that anode right at the focal spot. Okay, and we're going to develop X-ray photons. Okay, you'll note that this is the anode, this little red thing here. Sorry about my drawing. But you'll note that there's an angle right here. Okay, it's not a flat deal. There's an angle to it, right? And that's what we call the focal spot or the target of the anode. Now, you may think to yourself, geez, all that energy and all that heat hitting that one spot of the anode, man, that's a lot of pressure right there. And it is. Now, we combat that though by rotating the anode. Okay, so that anode is actually rotating 3,000 times a minute. So it's really moving. So when you walk in and you hit a rotor on your X-ray machine and you hear the X-ray machine start making a sound, that's actually that rotor turning the anode. Now, the reason we do that is to allow those electrons to hit all the way around the anode tube versus just one spot. Okay, it really, really helps us make it so our X-ray machine lasts a lot longer. If we were just hitting the same spot every time, we would have some major pitting and cracking of the anode, and our images would just look like crap. Anyway, starting out, there used to be a non-rotating anode. It was called a stationary anode. And it did work, but the longevity of the machine just wasn't good. So we went to a rotating anode. And when I say we, I mean people a lot smarter than me, but I'm just talking about it. So you may ask yourself, how on earth did we get the anode to rotate like that? So we use a rotor. Okay, that rotor is attached to a anode stem, which is made of copper. Okay, copper is a good conductor of heat, which is why we use it. Okay, now how does that rotor turn? This green thing, which my daughter, she seems to think that looks like a caterpillar, but it's not. It's actually called the stator. Something you'll need to know, S-T-A-T-O-R, stator. Okay, it's some magnets that actually use electromagnetic energy to turn that rotor 3,000 times a minute. Okay, there's actually ball bearings that wrap around the rotor. Those are made of silver-plated ball bearings. And the reason they use silver-plated ball bearings versus liquid is because liquid actually produces gas. And we don't want any type of gas within the X-ray tube. Okay, that's one thing. And silver is a good heat dissipant. It dissipates heat very well. Kate just looked at me funny. Anyway, so yeah, ball bearings are used to help rotate that rotor along with the electromagnetic stator, right? I did mention that the filament and the anode are both made out of tungsten, which has a high melting point, 3,000 degrees Celsius, which is really getting up there in heat. And like I said, the atomic number is number 74, in case you wanted to know. Okay. Okay. Now, the inside of the X-ray tube is completely devoid of any sort of gas or liquid. Okay. It's actually living in a vacuum. Have you ever heard the saying living in a vacuum? Well, the inside of the X-ray tube lives in a vacuum. There is no air in there. If you were to stick your head in there hoping to get a breath there, you'd be in trouble. Okay. But no air or gas within that. And that just allows the electrons to go freely to the anode. Okay. There's nothing in the way. So, and the X-ray tube itself is actually encased in glass. Okay. It's a very sturdy, heat-resistant glass. A lot of people have described it as a Pyrex type gas or some type of Corningware. It's a it's a glass that is very heat resistant and strong. Okay, so on the outside of the X-ray tube, we have what we talked about before, the metal outside casing of the X-ray tube, and that is actually bathed in oil. Okay. So if you were to take a lid off the actual metal part of the X-ray tube and look in there, is what you would see is a bunch of oil along with the glass X-ray tube. And yes, the oil is in there for a reason. The oil helps dissipate heat. If you've learned anything throughout this little thing, is X-ray tube develops a lot of heat. Okay, and it dissipates a lot of heat. All for that 1% of X-ray photons that we get out of it. Okay, just very important that we remember that inside the X-ray tube is a vacuum and completely void of gas. Okay, so down here we see that the X-rays hit this anode focal spot right here, and the X-ray photons are actually funneled down through a window down here in the X-ray glass. Okay, it actually allows X-ray photons to go through there. There's actually a couple filters there, and is what the filters do is they actually take away or inhibit the weaker X-rays from passing through. So once we get to the collimator here, we've got good, strong X-rays because all the weaker photons have been eliminated by a filter right here in the glass area. Okay, you'll know that you can kind of recognize the collimator. Okay, if we went out in the X-ray machine and looked at it, it's the box that has the knobbies on it, right? It allows you to open and close your X-ray tube to eliminate beam or add beam to your X-ray. Okay, so really neat setup. Okay, we're able to collimate down to the millimeter of what we want to be able to see, and that X-ray tube is only going to give us that much X-ray photons, and I think that's awesome. Okay, the people that come up with this are very, very intelligent people, and I'm thankful for them. Just for the fact that radiology has come a long way in the last 100+ years. The person that come up with X-rays, Röntgen, He's a pretty smart dude, and they went through a lot of health issues just to bring us radiation, uh, and I'm thankful for that. Anyway, so that is the X-ray tube in a nutshell. Okay, I would like to explain a little bit easier, and I think I did a pretty good job on how it works. However, take some time, study this, look at it, ask questions. If you don't understand a certain part of how the X-rays are developed, please let me know. I'm here to answer questions for sure, and keep looking forward to the videos coming out. There are some changes that are going on. We're gonna do a lot of neat stuff to help you guys learn this stuff. And it's pretty exciting. Anyway, thanks for stopping by today, Sarah. I hope this was helpful, and everybody else as well. Please don't hesitate to ask me any questions. I'm here for you, and I appreciate you. You guys are doing awesome. Keep doing great work. We'll talk to you soon.